So now
Thank you.
we will.
Thank you.
Thank you. Thank you. Thank you. So now we will move to the third session of the day. So we have the third session taken by Dr. Hanumantha Rao, the coordinator of this course. So let me give a briefing of Dr. Rao before he delivers his lecture. Dr. B. Hanumantha Rao is a faculty member of the School of Infrastructure, IIT Bhubaneswar since 2011. Dr. Rao received his MTech and PhD degree in Geotechnical Engineering from IIT Bombay, and he has completed BE in Civil Engineering from Osmania University. Prior to joining IIT Bhubaneswar, Dr. Rao worked as a postdoctoral research fellow at University of St. Catharines, Canada, and scientist at NPCIL Bombay for about a year. He has 10 years of teaching and research experience in the major research areas of geotechnical and geo-environmental engineering, with a focus on geotechnics and waste valorization, ground improvement, and development of sensor and sensing system for geosystems. Dr. Rao has supervised 4 doctoral theses and 4 is in progress, and he has 9 master dissertation to his credit. He is also author of about 45 journals of reputed publication, 28 conference papers, and 6 book chapters. Dr. Rao has secured a patent and has applied for 2 more patents based on the research outcome at IIT Bhubaneswar. So to list some of his major research contribution, Dr. Rao is successful development of geopolymer concrete using fly ash red mud slag as a binding material towards sustainable use of industrial waste or industrial waste byproduct. Proposing novel chemical treatment techniques to amend extremely alkaline waste for converting it into functional geomaterial. Stabilization of waste or soils by state-of-the-art MICP technique. Novel application of biopolymers and geopolymers for mitigating dispersivity and erosion problems in waste or byproducts. And also creation of unique database on swelling soils of Indian region, especially quantifying the montmorillonite content and relating the swelling parameters. So now I hand over the floor to Dr. Rao. Sir, please take over.
Yeah, thank you, Dr. Remya. So let me share my presentation. So is it visible?
Yes, it is visible. Yeah.
Okay. So good afternoon to everyone. First of all, we as a coordinators of this workshop, little sorry. So initially we plan to have another lecture by Ramki. So this is Ramki, which is dealing with the management of common hazardous waste. But unfortunately, so the engineer who supposed to deliver this lecture, so he got affected with the COVID, and the last minute he couldn't able to deliver any lecture, and he couldn't able to provide any kind of an alternative engineers also, which is a great loss. We both of you agree, but we try to compensate the same by another lecture. So this is on geotechnics and valorization of industrial solid waste. So let me introduce. So these are my research interests, and this whole research is done by a couple of my MTech and master students, so as you can see on the right side. So these are my masters and PhD students. So most of them have passed out, and some of them are still continuing, and they are on the verge of completion also. Now, so one of the highly sought topic is how to utilize the waste material. Now, when you talk about the materials, so different sectors are generating the different variety of the waste materials. Most of you well aware. So all these different sectors, which includes municipal solid waste. So a lot of experts are going to are going to talk about the municipal solid waste, then industrial waste, scrap materials, agriculture waste, and medical waste, so on and so forth. But this presentation specifically focuses on only the utilization aspect of industrial waste, that is industrial solid waste materials. And a few of the waste materials are shown here, which include coal ash, slags of different types, slags produced by the steel industry, slags produced by the zinc industry, copper industry, and red mud produced by the aluminum industry. So fly ash produced by thermal industry, so on and so forth. So the biggest thing is that the generation of these solid waste materials is huge in quantity. But if you look at their utilization, a few of the waste are being utilized in majorly. Suppose if you look at the fly ash, hoping 55 to 65% of its utilization is there across India. But if you look at, on the other hand, the utilization of the red mud, so the utilization maybe stands at 4 to 10%. In fact, it is less than 10%. That means 90% of this waste material is simply stored in the impoundment. Now, let us try to understand, because as the expert professors was clearly highlighting in today's and yesterday's lectures, see, unless otherwise you clearly understand the physical, chemical, mineralogical behavior, especially at the particle level, you cannot envision the proper utilization of these materials. But when you talk about these materials, so do they resemble in terms of with the soil, natural soils, or any other waste materials, or these materials are unique themselves? So let us try to understand all these aspects. Now, when we talk about utilization, the first question comes is, why should we go for utilization? So can we not keep these impoundments as a perpetual storage facilities? So the answer lies is, so it is not only India, across the globe, there are several catastrophic failures of impoundments that occurred and which has polluted permanently. So land area, as you can see from these pictures. So, so this is a failure of the red mud impoundment. So there are, it is in Hungary. The participants, can you please mute yourself?
So there are other data are also.
Hello.
Now, global warming is due to the accumulation of the global warming, the greenhouse gases.
Yeah, participants.
So the most blanket, the most particular blanket given, and that is how.
Dr. Hanumantha, I think this participant MCB has opened his mic. I think you can mute from your end if you are the host.
Yes, yes, I'm trying to.
It will not allow the heat to get transmitted into higher atmosphere.
Either you can mute all the participants. Simply mute all.
So the more the thicker the blanket.
So let me unmute myself. Yeah. So is this okay now?
Yes, 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 perfect.
Yes, it is perfect.
Yeah. So these are the few catastrophic failures of various impoundments that has been recorded across the India and across the world. But what would be the other problems that are posed by these waste materials? A few of them are has been listed here. The first thing is that the kind of health hazards that these waste pose. Then the biggest problem nowadays, which every industry facing, is acquisition of the land. Then the kind of the threat that is given to the environment by these waste materials. Then fugitive dust emission. Then the leachate which is being generated by these waste materials, and consequent pollution of the groundwater reserves. So these are a few problems. However, a few of the problems may be temporary, but most of the problems are perpetual in nature. But what is that aspect which makes them to be think of that yes, these materials can be utilized in civil engineering applications or in other engineering applications? So the first thing is there is a resemblance in the properties of these materials with the natural materials. But in all aspects, we may or may not be. Let us try to understand those things. But in addition to that, what are the other problems these waste materials pose? So the very first thing that comes into the mind is the strength. So we literally stabilize every kind of the waste materials and satisfy that yes, the strength is in compliance with the prescribed codal provisions. Then we say that yes, this waste is stabilized. But it is not only the strength aspect that poses a problem, but we also need to look into some other engineering aspects, which include so the collapse potential, the dispersion, and the alkalinity nature. Suppose if the collapse potential is high, then one can anticipate high amount of the subsidence or deformation. If it is, if the material is exhibiting high amount of the dispersion, so then you can obviously envisage some kind of the severe erosion problems. So both are not acceptable. So these two problems are, besides these materials are exhibiting the low strength. Now, another interesting thing is that if you look at the mineralogical and chemical aspects of the natural materials, so as we know, if you look at the sand, quartz is the dominant mineral. But if you look at the clay, either you can find it out kyanite or illite, or if you are dealing with expansive soils, you will end up as montmorillonite. But do we find these kind of the minerals so in these waste materials? So the answer is no. So if there is no comparison in terms of the mineralogical aspects, then how to understand that the mineralogical compositions cannot pose any kind of the threat to the environment or public health? The second aspect is the chemical or the chemical parameters, that is normally we read in the form of a oxide compositions. So now, if there is a distinction in the chemical composition, if there is a distinction in the metallurgical composition, then the question arises is, so in most of the time, we satisfy with using the single additive. But if a waste is posing the problems in terms of the strength, in terms of the collapse potential, in terms of the dispersion, then can we satisfy ourselves with simply amending with a single additive, or do we need to use more than one kind of additive? So this is the answer to be given to the all industry by the researchers. And this problem is especially popping up nowadays. Now, just to give a glimpses, so we try to compile the oxides compositions of different waste materials. So as you can see, so the material type, that is a waste material type, all are in solid waste materials, and the dominant oxide composition. So if you look at any natural material, you'll see that these four variety of oxide compositions are dominant. That is SiO2, Al2O3, CaO, and Fe2O3. And if you touch upon the people who are dealing with geopolymer concrete or alkali activation, especially, they specifically talk about the proposition of the silicates and aluminates, that is SiO2 and Al2O3. If these two compositions are dominant, they say that yes, these materials can be utilized for making the geopolymer concrete, or alternatively to develop the alkali activated concrete. So that also I will demonstrate in my presentation. But I think this slide should give you an idea about how the oxide compositions are differing in different waste materials. And this is contrary to the natural materials, because in most of the natural materials, you rarely see the odd man out, that is a different chemical compositions or oxide compositions. But if this is the case, how to deal with them and how to understand the impact of these differences in the chemical compositions on the engineering aspects? So just to give the demonstration, so we have compiled some data on compaction characteristics and try to analyze and make you understand. But the another question comes into the mind is, suppose if I take a similar type of the waste materials, can I say that yes, this waste itself has a some commonality, that is uniform chemical oxide composition? The answer is no. Suppose if you look at the red mud itself, so the one of the oxide compositions, that is Fe2O3, so it varies from as low as 24.5% to So as as 48.9%. So this is almost double. So then how to deal with such kind of a materials, because the material itself is distinct from the oxides composition. Then we commonly use a variety of additives to stabilize the waste materials, which include slag, the cement, gypsum, fly ash, lime, and so on and so forth. And if you look at the oxides compositions of these materials, so these additives are generally predominant with a particular chemical oxide. And we always look into how compatible these additive with the waste materials. And thereby we say that, yes, this waste is got stabilized or amended. But if there is no compatibility, or if there is a disproportionality between the chemical parameter of the additive and of the waste materials, then how to understand? Or if the variance is too much, so then how to come to a common conclusion? Because if this is the variance of the oxides composition in the waste materials, so can we fix to a particular content of the additive, say 4% or 5% or so on and so forth? So just to demonstrate, so I'm going to present the outcome of the research on the red mud. So these are from the physico-chemical mineralogical compositions of the red mud. So for those who doesn't have any idea, so red mud, so this is a waste material, but incidentally this shows some kind of the consistency behavior. So, but if you look at the fly ash doesn't show any kind of a consistency, though the majority of the particle fraction is a silt. But here also, in case of the red mud, majority of the fraction is a silt, but still it shows the consistency behavior, which is contrary to the fly ash. Similarly, other waste materials as well. And in terms of the oxides composition, it is dominant with iron. But if you look at any natural soil, these natural soils are dominant with silicates and aluminates. But here there are no silicates and aluminates. They are there, but in less proportion. So these are the elemental compositions of the different additives. And when it comes to the red mud, so this red mud is said to be the extremely alkaline material. But who is going to induce this extreme alkalinity to the waste material? That is, can we understand in terms of the minerals or in terms of the oxides? So you can see the minerals like sodalite, cancrinite, so hydrogarnate or tricalcium aluminate. So all these minerals induce some kind of pH to the red mud. Similarly, when you talk about the neutralization of the red mud, so unless otherwise you address all these chemical compositions like hydroxides, carbonates, by the aluminum hydroxides, etc., we cannot say that this particular waste material is completely neutralized. So the pH of the red mud generally holds between 9.2 to 12.8, but most of the time you can find it is above 11. So the challenge is, do we need to deal with the minerals or do we need to deal with the chemical parameters? So another interesting thing that we found is when we have tried to compile the compaction characteristics of different waste materials. So here you can see, so the lower spectrum of compaction graphs are belong to the municipal solid waste, while on the left side, so these are for other industrial solid waste materials. So if you look at the municipal solid waste, you can see the gamma D is quite less, but the optimum moisture content is substantially high. Similarly, if you look at the extreme left side on the topmost corner, so all these compaction curves are belong to the slag materials. These slags are produced by the steel industry, copper industry, and zinc industry. So interestingly, the gamma D is very high. So all these graphs were produced by the different literature. So if you look at these graphs, the gamma D is substantially high, but the moisture content is substantially low. And if you look at their chemical compositions, so these particular slags are dominant with a particular oxide composition. So the first one is SaO2, the second one is Al2O3, the third one is CaO, and the fourth one is Fe2O3. Similarly, so the soils which are chemically treated are the soils treated with the different chemicals. So these are intermediate. So the compaction behavior lies between the slags and the municipal solid waste. And other set of compaction curves are belongs to the red mud and zero site. So these are industrial solid waste materials. Here also you can see, so the dominance of the particular chemical oxide in these waste materials. And just to give more emphatic on compaction curves, so here we compile different compaction curves So these are the set of compaction curves of the slags, and this is for the riser, rice ascas, and these are the set of compaction curves for different materials. You can see, so this is a natural soil, and this is the fly ash, and this is a kaolin. So when you look at these pictures, one thing is clear. So the compaction characteristics of different materials are unique. Okay, so they don't follow the natural materials behavior. So if this is the case, so then which compaction curve do we need to believe it, first of all? And how do you make a comparison? So between waste materials and the natural soils, because when you think of utilization of any waste material, the first thing that comes to the mind is, can we able to compact this material, or can we able to consolidate these waste materials? If you consolidate, and would it show the least amount of the consolidation? So again, the further complexity comes is, so here my students have done some compaction characteristics of the red mud, so which is extremely alkali. Now, the interesting fact is that when we have done the standard Proctor compaction test on a similar and identical samples, we never got unique value of the gamma D or OMC. But when you have done the modified Proctor, somehow we got the consistent values of the gamma D and OMC. But if you look at the initial portion of these graphs, so there is some kind of a sensitivity of this waste to the moisture content. We don't know what is happening. So these are the things which we need to understand. Now here, if you compare the standard Proctor and modified Proctor, one thing is clear. If you want the consistent density value, you need to opt for modified Proctor rather than the standard Proctor. So again, so we also try to compare the compaction characteristics red muds of different origin across the globe. And you see, so the OMC varying from as low as 12.5 to as high as 35%. The higher side is on the higher side of the natural materials, and the lower side matches with that of the natural materials almost. But one thing is clear. So there is a variability in the compaction characteristics of the red mud. So you may take the same origin or different origins. So then, so this is a simple compilation of the gamma D value as well as the up to moisture content value of the different waste materials. So you will notice that the OMC of as low as 7%, as high as 130% is possible because these are officially reported, and gamma D max of as low as 4.2% and as high as 23.2% is reported and are possible. Okay, so if these are the extreme limits, so then how to compare these gamma D and WOPT values with different standards? So you need to understand. Now we also made an attempt. So though it is practically not feasible because to compare a physical property with the chemical property, but we try to understand. Would there be any relevance between the oxides compositions with the gamma D value or OMC value? So interestingly, we got some kind of a trend. Though physically they don't make any kind of a sense, but they can give you some kind of an indicativeness. So if SiO2 content is very low, so is other chemical oxide composition impacting the density or other characteristics? So that we can able to interpret. So if it doesn't make any kind of a physical interpretation, sorry, physical sense, then you have to make some kind of interpretations in other form. Now the thing is that if you look at the silica, so most of the particles are spherical in nature, but they are passive to the water content. They don't absorb a lot of amount of water. And if you look at the particle size, the typical SiO2 content is 5 to 20 nanometer, and most of the SiO2 is in powder form. So another interesting thing is the aluminum. If you look at the aluminum particles, they are not spherical, rather they are a flat shaped particles. So with the particle size of less than 50 nanometers, and more than that, see they are also passive to the water. Now you try to understand. The Al2O3 is a platy particle, SiO2 is a spherical particle. Now, would they behave in a similar way when I do the standard Proctor or when I do the modified Proctor? Or if I, now the question comes here is, suppose the elaboration comes here. Suppose if the waste dominant with the Al2O3 is used in the real field, and same if the waste dominant with the SiO2 is utilized in the real field application, would they behave in a similar way to the roller compaction? So someone asked you the answer to this question. So in that sense, we try to correlate these oxides compositions with the density characteristics, that is MDD and OMC. So here MDD is decreased with the Al2O3 content, but increased with the moisture content. And similarly, so we also try to correlate with the iron. Interestingly, though SiO2 and Al2O3 are passive to the water, but Fe2O3 is active to the water, because whenever iron particles are immersed in water, a kind of a monolayer of water film forms all around the Fe2O3 particles or iron particles. So that's why Fe2O3 is this iron is usually used as one of the adsorbent materials. And here also you can see the particle shape of the iron particles. Few are in spherical shape and few are in needle shape. So, and interestingly, when we try to correlate the Fe2O3 with the gamma D, so there is increment and maybe constant or maybe decrement. And similarly with OMC, it is decreasing with increase in the iron content, and thereafter either it's becoming constant or we can say so decrement, then followed by the increment. So the last one is the CaO content. CaO is usually said to be the pozzolanic, so it is highly reactive with the water. So it is basically develop some kind of the hydration reaction the moment you add the water to the any CaO. So this is the basic reaction mechanism. So even in case of the cement also, that means it is active with the water. So when we try to correlate the CaO with the density, so we found increase in gamma D with increase in the CaO content, and similarly decrease in the OMC with increase in CaO content. So now with this, either can we say that so as against earlier said to natural soils. So when you deal with the natural soils, so it is well proved that so the compaction characteristics are influenced by the compaction effort as well as the particle diameter. But so when we are dealing with the waste materials, can we also include another parameter that is to be looked into is dominance of the oxides composition or dominance of the mineral content? Because if you look at the spectrum of these compaction curves, so the point is well proven. And these are the different guidelines, which include IRC SP58, IRC SP20, IRC SP72. They give clear guidelines on what could be the minimum density or optimum moisture content. So behind which only these waste materials shall be used in the practical application. Suppose if you look at IRC SP58, so this code specifically deals with the fly ash and which prescribes the minimum density values, density value of 9 kilonewton per cubic meter, and in between 9 to 16. If it is higher, it is well and good. And OMC between 38 to 18%. 38 is C. 38 is on the highest, although 18 resembles that of the natural materials. Similarly, IRC SP20 2001. So this prescribes the guidelines for earthen cover as well as the subgrade or earthen cover. So you can see in case of the fly ash, so the density is as low as 9 kilonewton per cubic meter is acceptable. But for earthen cover, suppose if you want to use the waste material as earthen cover, that density should be sufficiently high. So that should be as high as 15.2, and for subgrade, it should be as high as 17.5. Now, when you make the comparisons between the previous set of the compaction curves with the prescribed guidelines, you can clearly notice that definitely most of the waste materials doesn't fall under the acceptable criteria. So in a first instance, so they will be eliminated to be utilized in a practical aspects. So this is one of the fundamental reasons most of the waste materials are stabilized or amended. These are the different codes and applications, different codes and their prescribed gamma D and OMC for different applications, for different materials as well. Fly ash, earthen cover, and application includes subgrade, or embankment, or road, or foundation. So we can take up any kind of an application. Now, so since we understood, so amendment is necessary. So we also try to amend the waste materials. So one of the things that we exercise is we try to amend the red mud with the biopolymer. So here we use two varieties of the biopolymers. One is Gorgum and next is Jandangam. So both are natural products. We try to amend or use between 0.5 to 4% proportion. So these are the compaction curves of red mud amended with Jandangam and Gorgum. So compaction you can see. So with increase in the content of the biopolymer, so there is a decrease or increase in the OMC or the gamma D. So there is improvement, decrement in the gamma D, but increment in the OMC. So that means, so these biopolymers showing some kind of affinity to the water absorption. At the same time, there is a decrease in the gamma D. But if you compare the highest and the lowest gamma D values, so few gamma D may fall within the acceptable limit of the codal prescriptions, and some others may not be followed. And these are the strength improvement. Now, if you look at any IRC code, and when you talk about the stabilization, we simply talk about what would be the strength improvement at 7th day. But will the 7th day strength remain constant over a longer period of time? So that also need to be ensured. So therefore, what we try to do is we try to determine the strength in the longer term, not only in the short term. So here the strength which has been measured over a period of time has been shown: 7 days, 28 days, 45 days, and 90 days. Sorry. Yeah, so these are the strength characteristics, basically stress strain behavior. You can see. So there was a significant improvement in the strength from 7th day to 28th day, but thereafter it almost became a constant till 90th. So these are the strength results and of red mud amended with biopolymers, Jandangam and Gorgum, and their comparison. So to make sure that they'll be utilized for a particular purpose, say in the road applications or the embankment purpose or any other civil engineering applications, as per different codal provisions across the globe. So we try to compare with the Chinese code, Australian code, our IRC code, or Federal Highway Authority code, or the guidelines provided by the different people. So it meets few of the guidelines, but it doesn't meet the other guidelines. So then next alternative that we look is red mud is a highly alkaline material. While if you look at most of the literature, they simply suggest that can we not neutralize these things with the simple NaCl and HCl. So these are the compaction results of the red mud amended with NaCl and HCl. Here the question comes is, so first thing is these chemical additives do not able to produce the consistent gamma D values or the YMC values. The second thing is when we have added these NaCl and HCl to the red mud, yes, they could able to neutralize the red mud. But the problem comes is when you are adding the chlorides, the chloride content is exceeding that of prescribed limit of IS codes. So you are ending up the pH problem, but you are inviting the chlorides problem. So in fact, it is easy to deal with the pH neutralization rather than eliminating the chlorides. It's a really daunting task. It is really very tough to remove the chlorides from the waste materials. And the simple question comes to everybody's mind is, so can we not use lime or the gypsum or the fly ash to stabilize the red mud? So these are the results of stabilization of the red mud with different waste materials. So they are mostly passive to the red mud. So one thing we have concretely seen is we try to expect some kind of a reaction between the fly ash and the red mud, but to our means surprising thing, we couldn't see any kind of reaction between fly ash and the red mud. Probably you may have to introduce some kind of a catalyst to make a reaction bridge between fly ash and the red mud. So these are the compaction curves of red mud, and red mud amended with the fly ash in different proportions, and this is red mud amended with the lime content. So this is red mud amended with the gypsum. So here, these are the strength results. You can see, in fact, then erratic strength value of red mud amended with the gypsum. First of all, there was no improvement in the strength, rather the strength was decreased over a period of time. So it was monitored up to 1 year. So we don't know what was really happening inside it. So to understand that one, we try to grab the XRD results, which use a clear understanding about the mineralogical aspects. We try to see, is there any change in the mineralogical compositions? And as you can see here, there is a definite change in one of the component, that is ettringite. There is a formation of the ettringite. Usually people will say that if you find ettringite, it is a strength improving agent. But here, though we could able to find out the ettringite, but there was no strength improvement. That means something else is happening inside the reaction between the gypsum and the red mud. So this is to be explored. So these are the compaction curves of the red mud, but treated with the citric acid, because citric acid is a very weak acid, and it is also reported that this could able to effectively neutralize. But it is not only the neutralization problem as opposed. So unless otherwise, the compaction characteristics meet the codal provisions, so merely neutralizing the red mud paste so doesn't serve any practical purpose. So therefore, in order to verify, so whether is there any change in the compaction characteristics, so the compaction curves have been produced of citric acid so in different molarity. So we have considered 0.1 to 6 molarity. So behind that, we couldn't able to prepare any citric acid solution. In fact, we can able to effectively produce 2 molar citric acid solution only. Behind that, never ever try to attempt it, and we found that 1 molarity is good enough. And there was a slight increment in the gamma D value, but so there is a decrement in the OMC. Both are on positive side. So this is the general thing that is expected. So when we treat any waste material, we should see improvement in the gamma D, but decrement in the OMC, so that we can ensure least amount of the settlement. And so this is compliance with the standard codes. Suppose if we compare the gamma D and W of citric acid lime treated red mud with IRC SP20. So this is as per the recommendation. It is acceptable for the embankment and for earthen shoulders. So except 5% lime treated samples, all other combinations are acceptable. So this is how you have to make sure can we try to utilize this waste material for the practical purpose. But this is simply based on the application. So based on the testing for compaction characteristics. But there are other hell lot of things are involved. And these are the strength characteristics. So having proven that, yes, in terms of the compaction, it is meeting the criterion, let us try to understand in terms of strength improvement, will it meet the codal provisions. So here also, we try to measure the strength in the prolonged periods. So starting from 7th day to 1 year. So we have again noticed that, so from 7th day up to 365, the strength attainment almost became a constant after approximately 180 days. That means the strength improvement is very, very slow. That means you can say the reaction, something is happening within the waste materials, between the additive and the waste material, but the reaction is very, very slow. So now if the reaction is very slow, the question arises is, first thing is that as per the IRC code, it doesn't meet the 7th day strength or 28th day strength, but it may meet 180th day strength criteria. So then, so how to accommodate these codal provisions with the long-term strength? So there is a big question. So another important factor is, yes, I have stabilized the red mud with chemical additive. So these are the pH results. If you look at the different molarity of the citric acid, so 1 molar, 1.5 molar, 2 and 2.5 molar, and we also try to measure the pH post stabilization. And incidentally, what we observed is there is a rebound in pH. That means the pH is increasing post stabilization. Now the question comes is, there is a relevance between the pH and the leachability characteristics. So this is a very well known fact. But suppose post stabilization, if there is a rebound in the pH, what would happen to the leaching characteristics of these post stabilized red mud waste or any post stabilized waste? Will there be any leaching or there will not be any kind of the leaching? So if you look at, then you can see the leaching, sorry, the pH rebound curves here. So we try to monitor the pH rebound for again the longer periods up to 180 days. So there is a clear-cut rebound. We also try to quantify at what time it is becoming some kind of a constant or plateau. So up to 45 days, the rate of improvement in the pH or the rate of rebound is significant. And after 45 days, it's almost becoming the constant. That means, so chemical reactions are nearly becoming saturated post stabilization at approximately 45 days. 45 days. Then till the 45 days, so how to ensure that there was no leachability of the harmful chemicals or there was no other consequent engineering properties change within these 45 days. So this is another quantification. So that is RRP, that is called the rate of rebound against the molarity. So the rate of rebound is slightly high for 1 and 1.5 molarity and low for 2 and 2.5 molarity. So these are all the quantification results for red mud treated with the citric acid. It is not only the citric acid, we also tried to neutralize the red mud with oxalic acid, then oxalic acid along with the lime in different combinations. So at the end, you can prepare this kind of a table. So this is simple compliance. This will give you very good picture about how to assess whether my treated waste materials fall or say yes, this treated waste material is acceptable or not. So these are the different engineering applications, and these are the different codes which describe minimum compaction, minimum UCS, and minimum leachability. So ensure that no harmful chemicals are reached. So you can keep on ticking that yes, it is meeting as per the IS 1498 for the subgrade or embankment. So in terms of the compaction or in terms of the strength. So this is again the same table. So here what we try to is we try to incorporate the application against the property of pre and post treated solids. So this is pre-treated and this is the post-treated, the waste material. If you look at this table carefully, so a few waste materials which are without treatment doesn't meet the criterion for practical application, while after treatment, so yes, so they are. For example, if you look at in terms of the permeability for embankment application, the without treatment the material doesn't doesn't fall under the category of acceptable. But post-treated, yes, it falls under the acceptability for the embankment application. So this is a beautiful table. So everyone should make. So this also includes compaction, permeability, index properties, strength, CBR, then settlement. Then additionally, you can also include dispersion, collapse potential. You can also include some kind of the leachability characteristics. Then this will give you a clear understanding how to assess the acceptability of the waste material for different engineering applications. The second aspect, that is another utilization of the waste material, is alkali activation or geopolymer. So the concept of this one is popping up recently. So I will try to quickly conclude this one. I don't need to re-emphasize geopolymer or alkali activation. So these are said to be the green materials, and the alkali activation or geopolymerization is possible for those waste materials which are rich in silicates and aluminates. So, for example, those materials like fly ash, slag, red mud, metacrylene, rhesus gas, etc. And here, the geopolymerization or alkali activation involves the activation of waste materials with alkali solutions like sodium hydroxide or sodium silicate. So, but you need to fix the concentration or the molarity of the sodium hydroxide and the molar ratio of sodium silicate to sodium hydroxide ratio. And when you add these alkali solutions to the waste materials, these are the different reactions so that can occur inside it. And at the end, what we get is the hardened product that is called as the geopolymer concrete or alkali activated concrete. So these are the basic steps involved in the geopolymerization or alkali activation. And so this is the major distinction between development of ordinary Portland concrete versus alkali activated concrete. In case of the ordinary Portland concrete, we use natural materials, thereby we make cement. Then this cement is used to bind the waste materials. But in alkali activation or geopolymerization, so we exclusively use only the waste materials, and these waste materials are activated with the alkali solutions like sodium hydroxide or sodium silicate. And as a result, we will get a hardened substance that is called as geopolymer concrete. However, the end product physicochemical mineralogical characteristics must comply with the ordinary Portland concrete, because for which all properties are very well established and proven, and all codal guidelines are available. And these are some so real life applications of the geopolymer concrete across the world. And there are two things that are basically involved in alkali activation or geopolymerization. There is something called as a low to mild alkali activation and high alkali activation. So under what circumstance we should exercise low to mild alkali activation or high alkali activation? Suppose if the waste materials are dominant with only silicates, then you can go for low to mild alkali activation. But suppose if they are rich in silicates and aluminates, then you must go for high alkali activation. And when you add these alkali solutions, this kind of gel formations you can notice. So then, because there is also a fundamental question to most of the students or the viewers. What is the fundamental difference between alkali activation and geopolymerization? Because if you look at any geopolymer presentation, so this is the fundamental question comes to the picture. So I hope this slide will clear you that doubt. So fundamentally, this is compiled from the literature. Alkali activation means activation of calcium-rich raw materials, while geopolymerization means activation of calcium-poor raw materials. And here also it has been given what are the calcium-rich materials and calcium-poor materials. For example, if you look at the metakaolin, this is calcium-poor material. That's why if you look at geopolymer concrete, most of the concretes were developed using the metakaolin. But typically, when you try to use the waste materials like fly ash or the slag, they typically fall under alkali activated materials because they are rich in some amount of the calcium. Then activating solution of moderate to high alkalinity in case of the alkali activated, activating solution of low alkalinity. Especially low molarity of sodium hydroxide is used in case of the geopolymers, and high molarity of sodium hydroxide is used in case of the alkali activated materials. So there is a binder paste formation in case of alkali activation and polymeric framework in case of the geopolymers. And these are the different gels that form in alkali like the CSH and CH, and this is in case of the polymeric network of aluminosilicates in case of the geopolymers. So this is the fundamental distinction between alkali activation and geopolymerization. And here also, as I emphasized about the influence of the oxides composition, one of my PhD students tried to correlate will there be any relationship between oxides composition versus strength development, because when you talk about geopolymer concrete, it is fundamentally dealing with the oxides composition only. So as of now, little preference is given to the mineral composition of the waste materials. And yes, as you change or as there is a variance in the oxides composition, they have a significant impact on the strength development. So you can see the huge difference in terms of the seventh day compressive strength or 28th day compressive strength. And this is the comparison in terms of the bar chart. So one typical thing that we can observe is, suppose if you look at the red mud is rich in the iron content, but metakaolin rich in others, poor in calcium. So, but if you look at the strength aspect, the metakaolin, it exhibits strength of as high as 60 megapascals, but the materials rich in red mud, so they exhibit a very poor compressive strength as low as 10 to 20 megapascals, almost 3 to 4-fold difference. So this clearly proves the influence of oxides composition on the strength development. This I will skip it because these are the results I'm going to talk about in my subsequent slides. So we try to develop some kind of a geopolymer concrete using the combination of the fly ash and GGBS. If you look at the fly ash, it is used as a pozzolanic material, but if you look at GGBS, it is used as a replacement to the cement. But they have some contrasting properties. The thing is that if you want to develop the geopolymer concrete exclusively using the fly ash, then you have to go for the elevated temperatures, because the polymerization reaction takes place only at the elevated reactions, or otherwise you have to wait for a very longer period of it. On the other hand, when you try to do the geopolymerization using the GGBS, the reaction is very quick. So there is some kind of workability issues also. So that means dealing alone with the slag, there is a negative aspect. Dealing with the fly ash alone as some kind of a negative aspect. That's why the people normally exercise the combination of the fly ash and GGBS. While this combination is ideal in a sense, this typically avoids the requirement of elevated temperatures. So the alkali activated concrete can be developed at ambient room temperature only, however in suitable proportions. So for that purpose, you need to determine the optimum NaOH molarity and optimum content of sodium silicate to sodium aluminates ratio. So as I have highlighted, so here you can see if the GGBS content exceeds 50%, so there are some problems. So as the primary binding agent, it causes suction of the moisture out of the mix, creating very low workability and rapid setting in concrete. So that means we can't go the slag content of more than 50%. So here, so this is dealing with the design mix. So this is the crux of any geopolymer concrete or alkali activated concrete. So two binder materials are considered. One is fly ash, next is a slag. So these are the particle fractions and the specific gravity of materials. Then in addition to the fly ash and the GGBS, so since we are developing the concrete, we need to add the fine aggregate and the coarse aggregate. So these are the particle fractions of the fine aggregate and coarse aggregate. And we have considered sodium hydroxide and sodium silicate as alkaline activator solution, and water, that is the potable water. And so this is the gradation curve. So we followed the DIN A combined grading curve. So to select fine aggregate and the coarse aggregate. So here as a design mix methodology, we followed the absolute volume method, and for gradation purpose, DIN standard has been used. And based on the lot of initial trials, we have fixed the alkali activated solution as 200 kg per cubic meter, and the molarity of 14. So this was the 14 molarity was fixed based on the initial trials, and sodium silicate to sodium hydroxide ratio of 1.2. So all these containts were fixed based on the initial lot of preliminary experimentation. And when it comes to the most important thing, that is alkaline solution to the binder materials, we have taken 5 different ratios starting from 0.4 to 0.8. And these are the geopolymer concretes for different AAS to binder ratio. So these are the quantities of different materials, waste materials, as well as the fine aggregates and the coarse aggregates, as well as the alkaline activated solutions. And these are the press properties, that is slump. So this is fly ash alone, fly ash and slag, fly ash, red mud, and slag. So these are the strength curves at different curing periods. So the compressive strength on the 3rd day, on the 7th day, on the 14th day, and the 28th day. As you can see, there is a significant improvement in the compressive strength from the 3rd day to 28th day. But of course, there was a continuous decrement in the strength with increase in AAS to binder ratio. But a minimum strength of 20 megapascals was ensured even at very high AAS to binder ratio of 0.8. And these are the tensile strength characteristics. And so these are the flexural strength and elastic modulus. Yeah, so that's what all about my presentation. So just as a closing comment, so there are a lot of questions than the answers, but rigorous efforts are required. Several varieties of additives are available, and several variety of additives need to be explored for positive utilization of the different waste materials. And sometimes when you are dealing with a particular waste material, a single additive may not be sufficient. You may have to look for the combination of more than one kind of additive. However, we need to ensure their compatibility in terms of the oxides composition and in terms of the minerals. So amendment seems to be one promising thing for waste valorization. Similarly, alkali activation also seems to be another promising the mechanism by which we can augment the utilization of the industrial waste materials. So thank you.
I would request participants to interact with Dr. Rao if you have any queries.
I have a query,
Yeah.
ma'am. Thank you, Dr. Rao, for this wonderful presentation. It was very informative. I want to ask, in red mud, if you're using it as alkali activated material, we already have a high amount of sodium hydroxide in red mud according to the process. So do we need to add sodium hydroxide for its activation?
Yeah, so this is very interesting question. So initially we also thought that since the pH is very high, so we don't need to add the sodium hydroxide in it. But when we have added only sodium silicate solution, we didn't find any improvement in the strength. So at the end of the day, we had to ended up in adding the in fact very high concentrate, very high molarity of the sodium hydroxide. So in fact, we also surprised to see this thing. This may be due to the fact that most of the alkalinity at the pH, so that is available because of the leaching of the hydroxides from the structural chemical parameters, but over a period of time, which are not ready-madely available for alkali activation reaction.
So one more question I wanted to ask. So have you have mentioned briefly the amendment of red mud with gypsum
Yeah.
and formation of etrinites.
Yeah.
Have you studied the change in pore structure of red mud due to formation of these etrinites?
No, unfortunately, we did not do any kind of microstructural
Oh,
analysis because see, we did not gain the enough strength. So we
did
were
not gain enough strength.
so we were clueless what to do.
Okay. 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 Thank you. Thank you. Yeah. One
Yeah.
more thing. The salinity, etc., with gypsum amendment, salinity and electric conductivity of the pore solution. How does that come out to be?
Salinity we did not measure, but gypsum found to be an effective agent for reducing the pH
But it
because
might increase the salinity because it also has its own its high ion EC itself it has.
yeah, true. I agree with you, but we did not measure the electrical conductivity of the salinity.
Okay, okay. Thank you very much. Thank you very much for the wonderful presentation. It was
Yeah,
really enlightening.
thank you.
Sir, I want to ask a question.
Please.
Sir, you have taken NaOH. Sir, why not you have chosen other alkali like KOH or other than NaOH? Why you have not chosen?
Uh, First thing is that KOH is expensive than the sodium hydroxide
Okay.
because even when you are using the sodium hydroxide itself, so the cost is slightly going on higher side. And if you try to utilize the KOH, so it will further increase. So this is the fundamental reason we try to end up using only the sodium hydroxide instead of the KOH.
But sodium hydroxide is plentifully available in red mud already.
It is true. As I answered, it is available, but in what form we do not know. Because suppose if you look at the presentation, there was a rebound in the pH, and that rebound occurred uh, up to 90 days. That means from the structural level, there is something which is leaching out over a period of time. Okay, that may be hydroxides, that may be carbonates, and that may be any other chemical. So that means most of this alkalinity at the pH is because of at structural level. While when you do the alkali activation, it should be instantaneous reaction. It cannot be like a 90 days or 120 days.
Actually not instantaneous, but it takes some time, like 7 days, or it takes some time.
True, it takes some time.
Okay.
But anyhow, that is to be explored in depth. I don't have any ready-made answer right now. So this is what is the observation we made it. So that need to be further explored.
Yeah. Okay.
Thank you.
And Dr. Rao, thank you very much for your elaborative presentation. I have a small question related to the neutralization with acids, neutralization of red mud using acids. So we are you have performed tests using high molar pH like 2 or 3 molar, whose pH is literally very extreme at extreme levels, approximately 0 sometimes. So in that case, it might so happen that few of the minerals which are there in your the red mud might get diluted in these acids. So what is your take on this kind of issues? Are there any investigations on this?
Yes, we try to identify any change in the mineralogical aspect or even chemical aspect also. Mineralogical by conducting the XRD and chemical by qualitative by EDX analysis. Yes, there is a change in mineralogical composition. In a sense, there's a lot of minerals which are getting dissolved. Okay, few of especially red mud is rich with sodalite. So something is happening to the sodalite content also. There are reactions found in sodalite, tantalite, and small amount of calcium which is available, and even for other minerals. But literally nothing happens to like hematite, boehmite, goethite, etc. So nothing is happening to the minerals which are belong to the iron family, but something is happening to the minerals which are belong to the what do you call titanium family or the calcium family.
Okay, then what is the physiological significance if we go for a field scale application of these experiments?
Physiological, in a sense, I cannot give you any concrete answer unless we literally demonstrate in the field. Okay. Yeah. You can see these aspects in a different way. For example, we have also understood in terms of the consolidation. Well, of course, even after treatment also, it showed means trivial amount of settling. So that is the positive side.
Okay, thank you.
Subhendu from Vedanta Lenjigate, sir.
Yes, Subhendu.
Sir, actually, I want to know, sir, the percentage of lime, fly ash, and gypsum added with red mud for stability point of view.
Actually, we have done with lime and citric acid or oxalic acid. We did not do with the lime and fly ash because, as I told, we did not see any kind of reaction between the fly ash and red mud. Because one is alkaline material, next is nearly neutral material. It's not neutral, either acidic or slightly base material. So we did not see any kind of a chemical reaction between the fly ash and this one. But if we add the lime, so this physically encapsulating the red mud and the fly ash, but the lime is reacting with the fly ash. That's a posidonic reaction, as you can see. But this lime also, suppose if you look at the chemical compatibility between the lime and the red mud, and again both are base, both the pH is above 11. Okay, but the certain combination that you told we did not exercise.
Sir, whether we use lime grit instead of lime?
Lime grit, I do not have anything. This I'm working on it right now.
Sir, actually, fly ash and lime grits are much more available with our plant, but only we have regarding this gypsum. And if we add this for red mud and we may utilize for a dry work, then it go for the much more stability than the other waste material.
It is true. It is true. On this topic, I'm trying to work. So because of this pandemic, we could not able to produce any results. So, but hopefully, once everything is resumed to normalcy, I could concretely give you some kind of results. No doubt in it.
Okay. Thank you, sir.
Yes, yes, and thank you so much for posing such a valuable question.
Thank you, sir.
Thank you, sir.
Yeah, thank you. So thank you all. So I think we came to the end of the today's session. So can we formally end today's session?
Yes, sir. So you can just inform, like tomorrow again, we will start the session at 9:30.
Yeah.
Schedule. We'll have 3 lectures tomorrow.
Yes, yes. So we request everyone to join Valid Advance at 9:15. So thank you all. So thank you so much.
Thank you, all the participants.
Yeah, thank you all the participants. See you tomorrow.